Well, welcome everyone. We'll get straight into breaking and fixing Unreal, an engineer's guide to problem solving. So let's go through the agenda quickly. Today we want to look at how we're going to identify problems, validate them with data, and then apply some practical debugging strategies, all while balancing real-world constraints that we're all familiar with, so your deadlines, platforms, and in our case, the impact we have on client projects. So it's not just about fixing things though, it's about how we approach problems systematically and how we use profiling and debugging tools to validate our assumptions and really just build up a culture of thoughtful and resilient engineering at Prismatic. So very brief intro, I'm Hayden, I'm COO at Prismatic Studios. I'm also a software engineer by trade. Prismatic is an Unreal Engine technical consultancy and co-development studio based up in Auckland. We work with clients all around the world helping solve complicated issues and problems in Unreal Engine. So a bit of a shameless plug, if you need help in Unreal, building a game or interactive experience, now you know who to come to. We also work closely with Epic Games as an Unreal Engine Gold service partner. And we're also an Epic Pro support partner, or formerly UDN, so you might have seen us on there too. It's more than just fixing bugs, as I alluded to earlier. It's a process of understanding, diagnosing, and then resolving complex issues, which is especially important when symptoms are unclear or misleading. So it's about using the right tools and asking the right questions and staying methodical. In the case of Unreal, it's also a case of knowing what the engine's doing and why, and not trying to fight it where possible. So I want to go through 4 broad buckets of problems briefly. First are your classic implementation and performance issues. These are really your classic things, like how things are not built right or they're built poorly. So you might be facing poor performance or memory leaks or just incorrect logic. Our engine system integration issues are times when things break down between systems, so think the likes of version upgrades or platform-specific edge cases, or you might be facing an issue with a third-party plugin or SDK. These can be tricky sometimes. You might be dealing with Unreal internals or external factors outside of your immediate codebase. So onto technical debt and architecture issues. These are your long-term pain points. You might have built something once and it was perfect, but over time it's become fragile and hard to maintain. And this kind of thing accumulates slowly, but then tends to explode under pressure. And then scope creep. So you might have had shifting requirements, or maybe your scope was just too large from the start. This is something that's just really difficult to keep on top of. So why do I bother going through these 4 buckets? Well, each of them involves a different subset of people that you're dealing with to solve them usually. So for our first 2, usually you're working directly with the engineers to solve these issues, working directly in code and reading through logs and profiling, debugging and whatnot. But for the latter 2, solving the problem is really only part of the challenge. The other part is convincing someone that the problem needs to be solved at all. So you're typically going to have conversations with your producers or leads or stakeholders, and you'll have to talk about refactoring or rethinking scope. So identifying the type of the problem is a good first step. It will not only set you on the right course technically, but also in terms of team communication and buy-in. So you're probably going to run into one or many or all of these types of issues throughout the course of a project. And as engineers, problem solving is really our bread and butter, but there are some times when a problem can seem overwhelming. So we really just don't want to take on the problem head on all at once. We should try and break it down. Get some clarity on what we know, and more importantly, what we don't know and what we can test. Because we really want to transition from this idea of I don't know what's wrong to I do know what's wrong and I also know how to fix it. So obviously what we want to do first is identify the problem. Sounds pretty obvious, but actually it's really easy to misdiagnose issues, especially in a complex game or a system like Unreal. If we fix the wrong thing, then not only we're wasting our own time and the time of others, but we're probably introducing new bugs too. So we want to ask some questions to frame the problem. Typical questions might be, can we reliably reproduce it? Environmental type questions, so can we do it locally, so only over a network? Does it depend on degraded latency or console stuff, or is it cooked versus editor builds and whatnot? Another important one is if a behavior has just come up recently, what changed in the system recently? We can look through our revision notes there, and that will set you on a good initial path. So I'll take a look at a bit of a case study, assisting a studio trying to track down a crash that occurred on shutdown of a recently shipped title. So this is relating to a background D3D thread. Strictly, it didn't affect gameplay, but it does affect crash statistics, and so the overall perceived stability of the application, so we want to get this out of the way. So the stack trace points us to the dynamic RHI system. Conveniently, we can't reproduce this locally. Call stack also unsymbolicated, which is fun. So what we did know is that it seemed timing related, so it could be a race condition between a game thread shutdown and that background thread, but really we just need more data before we can move towards a fix here. So we want to turn to our questions and sort of define the scope of this problem. Key one being, when did it start? So notably, this first began cropping up shortly after a 5.3.4 engine upgrade. Also explored crash frequency, which cropped up at this time and was intermittent for the most part, but could also spike during playtests. Notably, we ruled out hardware-specific issues, so it occurred on a range of GPUs, integrated and discrete. And so kind of mapping this crash frequency to the timeline, it became pretty obvious that this was a 5.3.4 upgrade thing, and it persisted through 5.3.5 as well, so that narrowed the engine changes down for us a little bit. So again, we can't repro this issue locally, so we worked with the team to really stress test and validate these shutdown paths. We focused on three main areas here: memory safety, thread lifecycle, and tooling. So first, we reviewed these background threads. We want to make sure that those related to rendering were shut down correctly, so we want to either correctly join them or terminate them before the engine systems and heap memory are torn down. Next, the crash also pointed towards a memory mishandling issue like a double free or a use after free. So we really want to audit that memory allocation destruction patterns, particularly around this D3D and RHI threads. So we can recommend some tools here as well: address sanitizer and optionally malloc stomp. These will catch things that are otherwise invisible typically. We also want to introduce thread guards and debug checks to really make sure that we're catching any late or unsafe memory access. So again, even though we can't repro this locally, we've built a lot of guardrails in place now to catch this issue. And ultimately, this did catch the issue, which was attempting to read an invalid memory address. So pretty typical error. Okay, so one common mistake we see a lot with teams of all experience levels really is guessing. It's pretty natural to want to jump to conclusions just based on symptoms rather than evidence. We really want to validate our own assumptions to confirm the root cause. We don't want to fix what looks wrong, we want to fix what actually is wrong. So another case study here, a multi-platform title. We were targeting a range of target frame rates depending on the platform, so we had to be quite intentional about how we profiled this. So we used a combination of Unreal's profiling tools and some platform-specific ones to identify exactly what our bottlenecks were and, more importantly, why they were bottlenecks. So, without this data, we could have spent days easily optimizing the wrong thing or missed critical issues entirely. So the great starting point here is Unreal Insights. If you're not familiar with it, it's a standalone profiling system that integrates really well with Unreal Engine to collect, analyze, and visualize data that's emitted by the engine. So what you can do as well is you can add more scoped trace events to drill down to expensive functions to really understand their internals. They integrate very cleanly with the trace system and Unreal Insights. With just a few macros that you can see, you can really easily mark up both engine and gameplay code to get a much clearer picture of where time is actually going. So first thing, to hit our target frame rate, we had to figure out what was slow to begin with, and really identify what areas of the game were causing performance issues. So good places to start here are your handy console commands, stat unit and stat FPS. From that, we can identify some problematic sections, and then really profile those and drill down into the why. It's also important to note that we can identify parts of the game and features that are taking a lot of time, but it's also important to know whether that time is justified. You know, it's all right for a feature to be expensive if it's actually worth it. So, Unreal Insights, it gave us 4 areas that we're able to drill into here. First of which was budgeting calculations for prioritizing features at runtime. The next is kind of all things AI, so AI controllers and animation blueprints and control rigs and whatnot. This was a significant chunk of time. Third, pretty interestingly, some functions were slower when the GPU was active, particularly on platforms with shared memory. And then lastly, our physics tick alone was taking up to almost 4 milliseconds of frame time. So there's some good news here. A lot was already done really well. And when we looked into the profiling data, there wasn't a single egregious offender and nothing stood out as that one, fix this and you're done kind of thing. But that made our job quite a bit harder, right? We needed to shave off small amounts of time across many areas rather than just getting one single big payoff. So to hit our 90 FPS target, we still need to recover just about 2 milliseconds of frame time, which is quite a lot when you're already running lean. So the question at that point is, what can we trim safely without compromising the experience? So you might notice a bit of a theme over these next few slides. The first common issue we identified were blueprint nodes like get component by class, being called on tick. So on the surface, it's a convenient node, but these can repeatedly copy data. Under the hood, it creates a new array, and it copies component pointers into it every time it's called. So the fix here, well, we moved this to C++, you don't strictly have to do that, and we retrieved the components once and used a T inline component array to keep this on the stack. Likewise, we also began pre-reserving memory for these arrays and used T inline allocators, again, to keep this on the stack. Similar story with has matching gameplay tags. Instead, we retrieved these once, cached them, and then we could run queries against that cache. So this is a pretty significant speed up. Using Unreal Insights, we can pinpoint these kind of things, but we still have to look at the blueprint to understand what the helper function is actually doing. And notably, just because we're in Blueprint doesn't mean we can forget about how memory is accessed and used. So with that, we reduced the cost of some of these functions by 80%, which is pretty good. These small wins really add up when we're trying to maximize our performance. Okay, the memory contention issue. So we noticed that there was a significant cost to accessing memory that wasn't local to the CPU. So for example, your shared CPU, GPU memory, this has introduced notable latency. What that meant for us though is that even small memory related optimizations had an outsized effect on performance. So for example, the same function, same code path, workload and everything was taking 10 times longer when the GPU thread was active. So for us, that was from 10 nanoseconds to 100 nanoseconds. So something typically maybe easy to overlook, but when you're chasing that 1 to 2 milliseconds of frame time, it really does matter. So again, similar story, we started caching frequently used values like structs and component arrays. We also built structs to bundle data between functions instead of fetching from the various classes each time. If you look at the engine source, you'll see this is done pretty commonly. All right, and our physics tick. So even though we had a lot of actors ticking in the during physics phase, we still had about 1.6 milliseconds of idle time on the game thread while we were waiting to start that post-physics work. So we had 2 options that we explored here. First was to move more work into the during physics tick to fill that gap, or we could reduce the duration of the tick itself. So again, our useful console commands, stat chaos and stat chaos counters, that led us towards some unexpected results. We had one level, it had few physics bodies, and that had a physics tick of 4 milliseconds. We had another level with many more physics bodies. It only had a physics tick of 2.66 milliseconds. So we can dig into Unreal's physics views here to find out what's going on. We found in the more egregious level complex collisions, objects with very large bounds, and static geometry marked as movable. So the first protocol here is to find the offending assets to deal with. You can use the content browser using a search term like collision perims greater than or equal to 500, and you can also run the console command collision.list objects with collision complexity, use complex as simple to find assets with your high complexity collision data. So we found the misconfigured assets, we could address them, and then we're able to reduce that physics tick to get us in budget. So, UE Insights. It identified dozens of these micro issues, if you will, that none of which were obvious from the get-go. So we combined that profiling with some blueprint awareness, C++ optimizations and memory management, and that let us claw back the performance we needed, 100 nanoseconds at a time. So, MemReport. This is great for memory diagnostics. In essence, it captures a snapshot of memory usage at runtime. It shows us what is in memory by assets, engine systems, streaming levels, whatnot, broken down by category and often by individual object type. It works by typing in MemReport into the console in Pi, standalone or builds, but you'll probably want to use the dash full flag to get a bit more of a detailed breakdown. It's worth noting just what MemReport is. Behind the scenes, it runs a collection of other console commands and just groups the output together. So you can think of it more of a static report. It's not a visual thing like Unreal Insights. Epic have also indicated that they're working on more memory management reporting in Unreal Insights, and that some aspects of MemReport aren't being actively maintained. But regardless, it's still a useful tool to have. A lot of times you'll discover that a single class, like a uTexture2D for example, is using way more memory than you'd expect, and MemReport can give you the list of exact instances that contributes to that. So again, if you're facing memory pressure or garbage collection hitches, MemReport is a great place to start here. So here's a quick example. We use MemReport to track down a tricky memory crash. A bit of a classic behavior here. Things are fine for a while and then they eventually fall over. Nothing really actionable in the call stack, so we turn to MemReport to build that picture for us. So a key thing we want to look at were allocation bins, essentially where and how much memory the engine thought it was allocating at the time. And since console memory can be quite tight and segmented, we enabled larger memory modes in development to get a clearer picture of what was occurring before the crash. So we saw that we were allocating 14 to 15 gigs of memory beyond the limit of the console. So this is a pretty clear case of over-allocation here. We could track this back to geometry caches, and at the time, experimental engine feature. These were actually leaking memory fairly aggressively, close to half a gig per instance. It's pretty egregious. So that became pretty easy to track down. At this time, we also found a memory leak in the engine itself in the RHI pull allocator. It was present in UE main at the time, so we reported it and contributed to a fix. So this wasn't just a project level win, but one of those times where MemReport made the engine a better place for everyone. I want to go through PICs briefly. This is Microsoft's performance tuning and debugging suite for Windows and Xbox using DirectX 12. So if you're dealing with those platforms, it's super useful to delve into low-level performance bottlenecks and really understand how your content is reaching the hardware. So it makes it essential for that deep kind of level of performance tuning. It's vendor agnostic, so it works on all GPUs that utilize DX12. And as of UE 5.6, it's supported directly via a little capture button in the editor, so there's really no excuse not to press the button. Generally, we use PICs as a render debugger, but more often than not, we also use it to rule out GPU-side issues. So I'll take you through a very brief case study as well. I will try very much not to get into the weeds on this, but in typical raster graphics, DDX and DDY instructions are handled by the GPU, but with Nanite, this isn't the case. Nanite relies on analytic derivatives wherever possible. If it's not possible, Nanite will render in 2x2 quads, which impacts our variable rate shading. So using the no DerivOps view mode, we could see that we were using the 2x2 quad rendering for almost every drawer in this scene inadvertently. So we wanted to prove two things. One, that we truly had derivative operations, and that these operations were caused by our material graphs. So Unreal Engine gives us great answers to what questions with these view modes, but Pix gives us the why. So yeah, that's right. So again, in the editor here, once we enable it, we can see we're using quad rendering for pretty much every drawer in the scene. With Pix, so we launch the package development project, but before we capture a frame, we'll want to set r.rhi set GPU capture options 1. This will export the markers and the names that we need to track down the drawers. So this is probably almost impossible to make out, sorry for that, but the gist is that Nanite wants to use samplers like texture, 2D sample grad, it passes derivatives explicitly. Samplers like texture, 2D sample bias will implicitly calculate derivatives. So we can see Pix here, we've selected the drawer for m_test triplanar 1, that's our material. We've also selected the world normal G buffer to visualize this call, and we care about the shader bound to it. It's also on the compute queue, just because Nanite base pass is compute shader based. So we investigate the shader itself. We see that it has a function. That function has a call to our texture 2D sample bias function. Compare that to another material in the scene with analytic derivatives. This uses texture 2D sample grad, so that's why our middle objects appear in blue. The one on the right uses both. So we can see, well, we want to answer a few questions. First of all, why are these derivative operations there? How are they getting into the shader? And what are our alternatives here? So again, the leftmost was using sample bias, middle using sample grad, and right a mix of both. So this pretty clearly ties it to the materials we're actually using. So we've proved it was due to our material setup. That's both the what and the why now. So at this point in time, we have pretty good confidence that we can proceed towards a fix addressing the materials themselves. Okay, and last tool I want to go through, Insight Aftermath. This is NVIDIA's GPU crash debugging tool. Again, it will tell you exactly what the GPU is doing the moment a GPU crash occurs. It's integrated as a lightweight C++ library that's supported by Unreal Engine. It really has minimal overhead, and it's lightweight such that you can even include it in your final shipped game if you so desire. The difference being with Aftermath compared to the previous tools that we've been looking through is that this has a focus on post-mortem debugging. So here it is, Aftermath. Again, we typically use this to investigate random GPU crashes using the GPU crash dump inspector. So the good first step here, again, I apologize, it's probably not too readable, is to check the exception summary under the dump info tab. So this will give you that high level view of where it went wrong. You know, maybe the GPU is hung, for instance, or if there's a page fault or whatnot. So if there is a memory fault, the next best place you want to look is the page fault section under the crash info tab. So here you'll see if memory was accessed out of bounds or if it was already freed, for example. After that, the GPU state section also helpful. It'll tell you what the GPU is doing at the time. So for example, what part of the pipeline was active, maybe texture sampling. And it's also worth noting that Aftermath identifies shaders based on code hashes, not your file names. So you want to configure your search paths for shader binaries. You'll usually find this kind of information in saved/shader debug info. Okay, so again, how do we use this in practice to identify these random GPU crashes when using Unreal under any circumstance? So you'll want to add the -GPU crash debugging flag to the command line, or in your project settings, set r.gpu crash debugging to 1. So in this given example, we can analyze a crash dump with Aftermath, inspect the GPU memory, registers, and other data at the time of the crash, and we can see that, again, in this given example, the cause of the crash was a fragment shader that was trying to access a resource after it had already been destroyed. So that will give you a page fault error. So when you're facing an issue, especially one that is a bit mysterious or intermittent, it's really important to strip the problem down when you're testing it. We want to eliminate as many variables as possible. If we can replicate the issue in a clean, minimal test level or even a test project, we're going to be far more likely to understand what's actually going on. This makes it much easier for yourselves or teammates or Epic or us to help. So another reason is that if the issue is not reproducible, how do you know that it's actually fixed? A fix that can't be verified isn't really a fix, and we can't really have any confidence that the issue is really resolved. So what we want to do, obviously, is identify root causes of a problem, and then the next challenge is actually fixing it. So something that's super important about addressing these issues isn't just about writing code. We want to understand the impact of the fixes that we're making. So let's look at some strategies and best practices to approach fixing problems effectively, but also safely. Something I want to introduce here is the idea that every fix has a blast radius. So, potential impact or fallout from a change we might make. Even really well-intentioned fixes can break other parts of the code base. So before we go making a sweeping change, let's assess the level of risk involved in making a fix. So there's a few factors that I think are good to consider here. One is visibility. Are we fixing something that's going to be visible to the user or perhaps a client that they'll directly see? Obviously, this is higher risk. Is the code or system that we're developing with complicated? Is it tightly coupled to other systems? This obviously will increase the consequences as well. Do we have confidence that we actually understand how the system works for a start? If not, that's pretty clear cut. And timing, I think this is quite a pragmatic one. Are we getting close to a milestone or a release? If we're making these changes late in that development cycle, we're going to carry a lot more risk. So we want to understand these factors before we put together a strategy. So for these low-level issues, we can pretty much proceed directly, right? So we can make the change, we can test it ourselves, have confidence that the fixed behavior behaves as we expect, and there are no side effects. For these sort of medium risk issues, we want to be a bit more cautious here. We want to perform more thorough testing, have other team members thoroughly review our changes, involve QA perhaps a bit earlier, and document heavily what we've done, just so that we can track this later on. And for these high-risk issues, where the blast radius is large, we want to start applying mitigation strategies here. So it's probably best to escalate review of these issues to your team lead or your senior engineers, just to make the most of your experience. And something that I would highly recommend is using feature flags or otherwise configuration toggles to control the rollout of a fix like this, such that if something does go wrong, we can pretty easily roll that back. So I'll go through a high-risk case study here. This is relating to player-saved data. Obviously, any situation in which we're adjusting player-saved data carries significant risk because it can significantly adversely affect the user experience. So there are a few things that we want to do in this given save system. We want to go from string serialization to custom binary serialization along with versioning. We want to compress save files using LZ4. We also want to add a code path that resaves all current user saves to actually enable this compression. So the third of which is the very scary one. So first of all, custom serialization. By default, Unreal serializes the save game in a string-like structure. It's not the most disk space optimized. The trouble for us was that the day zero build had gone gold with this method of serialization implemented, so we can no longer guarantee that we could go down the custom binary serialization path, so we had to handle both formats. Luckily, in UE, the archive versioning system, it's pretty robust. It provides an easy way to do this, and going to this new format gave us around a 16% reduction in save size, which we think we could have done a bit more, but we were being cautious here. So this went pretty smoothly. We handed this over to QA a few weeks prior to launch. It was tested rigorously. It went live in a day 0 patch, so we were relatively confident that the majority of saves should be on this newer version by default, but as mentioned, we can't really guarantee that. There's also not really a way to roll back this change, so we just needed to really test this heavily. Okay, it also became pretty apparent that save size was an issue on platforms with limited cloud backup space, so we opted to explore save compression here. Our go-to was LZ4. It's fast, so we're not going to experience the save hitching, which was a primary concern. Unfortunately, LZ4 natively in the engine is LZ4HC. This is running at its maximum compression setting, and it can cause a hitch while compressing our save files of upwards of 3 seconds. It does attain an impressive 14:1 compression ratio though, so that's pretty good. So on some platforms we would have just put this on a background thread. Problem was we had other platforms that were severely limited by physical cores, so it would have just resulted in a 3-second game thread stall. Obviously this is unacceptable for us, so we used the LZ4 files that were in the engine to adopt the non-HC version. We went from a 14:1 compression ratio to a 7.5:1, still pretty good, and it runs in under 50 milliseconds, which was acceptable for us. So we reduced the save file size, we minimally impacted performance, except, again, this was not in the gold version of the day 0 patch. So we couldn't guarantee that all save files were already compressed, which leads us to having to manually resave every save a user has ever made. This is definitely the scariest change we made here. It could break every save for every user on every platform. So for that reason, we really can't get this wrong. So what do we do here? First of all, we want to identify every situation that we could end up with corrupt data. So this will really direct where we spend our testing time. Additionally, we added a bunch of error injection to simulate potential failure modes during the resave to really make sure that the code path was well traveled. We also wanted to make sure that any kind of error was as recoverable as possible. So this is even including an application crash or a power failure. And this is more or less what we did. So we decided to handle upgrades by attempting to load an original save and generating a hash for that file. We can then deserialize it and serialize it again to a temporary location, and we can get a checksum from that temporary file that we can check the validity of. Then we load this temporary file, deserialize it, and compare it against the original save deserialized, and if they're valid, then we can write that deserialized temporary file back onto the original. And again, we load the original, deserialize it, compare it against the temporary file. If they match, we're good to clean up the temporary data. So this kind of pattern let us recover from power loss, general data corruption, and even logic issues in the serialization, although admittedly, if there had been logic issues, the game would have been unbootable, but we wouldn't have lost any data. So looking back, we could have done a little bit more, actually. We could have made it more resilient by utilizing a staggered rollout to really limit that blast radius again to a select group of users at a time. We could have built a few more robust integration tests to catch some breaking changes a bit earlier. And I think this is a universal truth. We could have had more time for testing, especially around some platform-specific quirks around file I/O. Okay, so sometimes the smartest fix is not to make a fix, but is to conduct a full rethink. A system can get unstable and overly complex, might be prone to breaking, and we might just be delaying the inevitable here. We might need to refactor or rewrite this, not just fix it. Even though quick fixes can feel productive, it can add to the long-term tech debt, especially if they're not properly tested. So, not every project can afford a full refactor, but if we get into this situation where the cost of maintaining this kind of a system outweighs the cost of replacing it, then it's time to stop these band-aid fixes and address the root cause. Something we encourage at Prismatic is a bit of a fix as you go or fix as you touch approach. So again, if you can't afford that full refactor, as you're touching bits of the code or tangential pieces, just bring it up to spec as you work your way through. So also, when we're making these sort of changes or committing to source control, we really want to document them well. It's not just for you. It's for the entire team, not just now, but also years in the future when the context of the change is long gone. The person that's reviewing the change then might have no idea why a random check was added and even what bug it caused or what it fixed in the first place. So we can help them out here. I've got a couple example commit messages here. We really want to be deliberate. So the second example is a great example of where it has practically no explanation, no traceability, and no way to know how the crash was actually fixed. And why did we include some work in progress level stuff here? I'm not too sure. So we also want to avoid the classic vague commit messages. I don't want to see any fixed issue or minor tweaks. Don't include just the what as well, but also the why. Future you and your team will definitely be thankful. Okay, I want to touch on modifying the Unreal Engine source code as well. This is something that can often be the right move, but it's important that you understand the trade-offs. These kind of changes can introduce potential merge conflicts. These kind of things can take hours or days of manual work to integrate upstream changes. It can also create a lot of friction onboarding new engineers onto your team. So there's a few situations where I think this kind of thing is justified. Maybe there's a critical bug fix that hasn't actually been merged in upstream yet and it's blocking your team. There might be a core engine limitation that's just necessary for your game's essential feature. You might have a proven optimization that gives you a real and validated performance gain, or you might be committing to a long-term engine fork, maybe a console fork, or an internal tech platform that you're planning on owning over time. So there are some best practices to follow here. It's best to start with a plugin or engine subsystem, if at all possible, and really only modify engine files when it's super necessary. We want to isolate changes into a few files or a few dedicated classes. We don't want to be scattering them throughout the code base. We want to document changes really well. So keep a change log and include the reason for code in the comments. I think Chris Murphy mentioned yesterday, it's a really good idea to have a huge comment block of engine change starts here and ends here to really make it super obvious. You'll also want to maintain a clean mirror branch of the release UE version. This is going to make it much easier to compare diffs and help with merging. I didn't realize this was in all caps, that's hilarious. But you should seriously consider perforce. Git can work, of course, but pretty much all of Unreal's tooling is built with perforce in mind, so it's going to make this kind of workflow much, much more manageable. And we finished way earlier than I expected. That's amazing. So I think we can take questions, but I hope this gave you insight into the kind of processes and tools we use at Prismatic, and hopefully you can take a few things home with you.
I was just curious if you managed to reproduce that crash at the start that you were like having trouble tracking down.
The shutdown crash, was it?
Yeah. Because later in the thing you said, oh, you have to be able to reproduce it to know if you fixed it. So I was curious if you got the reproduction.
Yeah, so our team couldn't reproduce it locally. We could validate that via the analytics it stopped occurring after the fix. So that's kind of good enough.
Close enough,
I think.
yeah.
Close enough is good, yeah.
Do you use unit tests for the validation of these fixes as well?
Sometimes, but not always, I would say. I I think more often than not we'd utilize QA, but I mean, like I said, unit test is something that we should have done a better job of using. It would have saved us a lot of time, I think.
You mentioned at the end in all caps that we should be using Perforce for like engine source control, but obviously they hosted it on GitHub, and I thought, like, my impression has always been that they want you to fork that particular repo using Git. So like, what are the trade-offs there?
So it's mirrored to Git, is my understanding. And if you ask Epic really nicely, you can get the Perforce credentials for the engine source.
Thanks.
Hey there. So you mentioned in your talk that once you get to a certain point, like bigger changes, you actually have this other layer, which is convincing somebody to let you do it. If you already done all your assessment and you think it is a good idea to do it, how do you go about it? What are the things that you bring to the table to somebody that perhaps is not technical to convince them that they need to invest time on fixing something?
Yeah, so typically if you explain the cost implication, that's pretty convincing. But I mean, there are some times when they're just not convinced and there's no way to change their mind, in which case it's a really good lesson for them. But I mean, you can only do your best, right? Explain what the practical impact it's going to have on the development timeline and cost in particular. And then, usually if you black and white outline what will happen if you don't do this, that usually gets the point across.
I was just curious, how far in your like testing and stuff, like, do you go with debug builds versus like test or shipping, that kind of thing? Because I find that that's kind of a thing you have to decide of how far you go with those kind of builds, like how far through playtesters or that kind of thing.
Yeah, I think anecdotally we would not often test with shipping until quite late. I don't know if that's fair to say, Keegan. Yeah, I mean, we get a lot more information not out of a shipping build. But I don't know if there's a correct answer to say. Even among our different projects, that changes project by project, the approach we take, especially depending on device or platform that we're targeting.
Thanks.
Sorry, I know I was far. I was just going to add, if you don't test with your shipping builds until the very end, if you've got check macros and you've got code in there that actually evaluates to something, it'll get compiled out when you ship the game. Don't ask how I know.
Yeah, do test your shipping builds. Yeah, I wasn't trying to imply don't test your shipping builds, but yeah, there's a balance for sure. All right, thanks everyone.